It's 1 o'clock, so let's do it. I first want to just highlight. Oh, awesome. Will's here.
Hi.
Will, can you finish setting up the GroupMe?
Yeah.
All right, sweet. This was my favorite anonymous feedback from this last week. Somebody just sent it in like an hour ago. But it's this Stack Overflow, this innocent Stack Overflow question asking about whether non-native English speakers code in English. And the first answer is... That was so good. Visible, eh? Let's just pass it around because I think there are people all over, yeah. All right, awesome. People are still coming in. I also want to who managed to do the bomb diffuse homework? Good number. Okay, sweet. How many of you actually did dependency injection to solve it?
I don't remember.
Some people, they did some inheritance and stuff. All right, cool.
I did it, but I did it by making a new MRO directly instead of.
Oh, that's cool too. Well, basically, I tried to make it so that there's only one way to do it, but that's impossible because there's so many different ways to print out that code. And so I just before starting here, I want to pull up Andrew's solution because he took a shortcut that I didn't think of. This is Andrew's solution. If this is, are you okay with it? Okay, good. So what he did, and this is not what I expected, but what he did is he wrote just this static global function called newTrigger, and it takes in self. But note that this function isn't in a class, so it's not exactly clear what self is right now. But either way, it takes in a parameter called self, and it's just this global function. And then he takes the explosives class, accesses the trigger method, and assigns it to this global function. And then when he calls trigger, nothing happens because he's reset the trigger method on explosives. So I totally failed to see this, but this works. So pretty cool. And you probably, you might not have thought to do this because there's actually a lot going on here. And the first thing is that this new trigger function was treated as a variable right here. And what's more is this method was treated as a variable on the explosives class. So there's actually some weird stuff going on here, and it's just so happens to be exactly what we're going to talk about today. So I just thought I'd use this to segue into the slides. So. All right, this is what we're talking about today, first-class functions. And so Andrew's solution works because Python has first-class functions. So we'll learn about what those are and all that stuff. One thing to note is I didn't come up with a group coding activity for today, so no need to get Adam out or anything. Sorry. Maybe we might end a little early. I don't know. But there's no group coding today. But the homework, which is due next Monday, I'm trying to think of some way to roll that into group coding. So please do your homework this week so that everybody can participate in the group coding next week. I'm not quite sure exactly how it's going to roll in, but it's going to roll in and it's going to be fun. So just do your homework for next week, and then we'll have some interesting group coding. But anyway, first-class functions. We're going to talk about the call function. This is another dunder method, so this is dunder call. We're going to see some examples, some really interesting recursion. And this interesting recursion part, I'm going to introduce this idea of a fixed point, which is kind of an idea that I just kind of made up. it's not really a thing. But what I'm getting at is that we're going to start digging down deep into Python and finding interesting behavior where we'll have some object, we'll perform some action on that object, and end up with exactly the same thing we had before. And so I like to call that a fixed point because you could keep applying this action over and over again and just stay at this one spot. So it's like a linguistic identity, so to speak. But anyway, I don't know, just interesting. We're going to talk about lambda functions, and this is going to start getting into functional programming, which is hard not to talk about when you're talking about first-class functions. And then finally, we're going to go over generator functions, which are not strictly first-class functions. I mean, they are, but I more just want to cover this because there's no better place to cover it, and it's really cool, and it might come up later. So, today is all about functions. It's like the function day. So functions, yeah. So in the first lecture, I mentioned that objects in Python are homogeneous and ubiquitous. Everything in Python is an object. And we even printed out the type of print, and we got built-in function, proving that even functions are objects. Well, so we're going to dig into that more. Because they're objects, you can assign them to variables, and you can pass them into functions and return them from functions. So let's see that. Let's import the mean function. And now we've got the mean function here, and we're referring to it by name. And we haven't put parentheses on, which means we're not calling the function, we're just referring to the function. So this is the function, and we're setting it to func. And so now, if we call func on some list, we get the mean of that list. So func is now a variable that also references this function. So this is an example of assigning functions to variables, and we can do this because they're just objects. Now we can reassign func to sum, and if we call that same line again, now we get the sum of the numbers. So what you can see here is we've got some really cool dynamic behavior. We could have a situation where, calling one function is really more of like an if statement, where what actually happens when you call this function depends on what happened before the function. So here, calling func did mean because we assigned it to mean. But we could have this assignment happen in some sort of switch statement, and then calling this function would behave like a switch statement. It would be really interesting. So very dynamic, very cool. And we can even check if functions are equal to other functions. So we've got func and sum. This should be true, and it is true. And the string representation of a function is pretty much what we saw on the first day. We can also pass them into functions and return them from functions because, again, they're just objects. So let's say we print func. Well, here we're passing func in as an object, and so it's going to get printed like an object. We print the string representation of this object. Now, let's do something more interesting. We've got a function, and it takes in a number, okay? And if that number is 0, we return mean. If the number is, otherwise we return sum. So here, this is a function that's returning functions. And so the way we call this function is actually with two sets of parentheses. And so a lot of, you don't see this very often, but this is how you have to call functions that return functions. So we've got this function, and we're calling it on 0. If num is 0, we return mean. So now this whole expression here, from the m to that right parenthesis, is mean. And so then we call it again. So you can kind of call functions over and over again if the function returns a function. And we get 2, just like we expect. If we call it on 1, we get 6. So this is what I was talking about with the kind of dynamic behavior of function objects. We can assign them, and then we have dynamic behavior Yeah, pretty cool. Does that make sense to everybody? It's a little weird, especially if you haven't done any functional programming before. You don't often see these like adjacent sets of parentheses, but it's totally possible. So, like I said, because so functions are objects, but if they're objects, then that means that there's a class for them, right? So it turns out that any class can generate an object, can produce function instances by just implementing call. So, all right, we've got a reverse function here. This is, I think, exactly the same function that I showed on the first day. We take in a string, and then we put the reverse of that string in out and return the reverse. And it works just like how we expect. Now, we could rewrite this as a class. So let's make a class, capital R reverse, and then we implement the call method. And because it's a method, we take in self, and then the string that we're trying to reverse. And then everything else is the same. So if we want to call this version of reverse, because it's a class, we first have to create an instance of the class. That's this. This is the instance of the reverse class. So this is an object, and this object is a function. So now we can call it again, other reverse, ABCD, and we get the reverse. So this is another way to write functions. And so what's happening here is when you call this function, what's happening is the dunder call method is being called. So the call behavior of instances of this class is defined by the dunder call method. So if we get the type of reverse, it's just a function, just like we expect. It's a function, we wrote it, it's a global static function. Now, if we get the type of other reverse, what do we expect? Anybody? Reverse, yeah. Yeah. So just because we implemented the call function doesn't make this instance different. It's still just an object, an instance of reverse. It just so happens to be a callable instance of reverse. Now, what if we get the type of otherReverse.call? Any thoughts? Function? So this is actually method, because the call attribute here is a method on this object. This is the object. This is an attribute. And when we call, it's a method for this object. Does that make sense? Now, how about this? Any thoughts? Well, remember earlier, the last class, I said you can call methods statically or non-statically. So this is an example of accessing the call method non-statically. We have an instance, a specific instance, and we're getting the call method of that instance. So this is a method. But here we have the class, and we're getting the call attribute of the class, which makes this a static reference. So when we print this out, this is just a function. If we were to actually call this method, put some parentheses here, we would have to pass in self, because this is a static reference to the call function. All right, how about this one? Any ideas? Does this even compile? Because here we just wrote a function here. We didn't write a call method. So is there even a call attribute of this? Who thinks there is? Who thinks there isn't? Okay. It turns out there is. Just because we didn't write a call method here, it turns out that if we write a function, like we did right here with the def statement, what we're actually doing is creating an instance of a function class, and that function class has this call attribute. So anything that's callable in Python, anything that you can put some parentheses after and call, will have this attribute, .dunder call. Now, if that's true, isn't this callable? This is a method, right? Couldn't we call this? Call has a call.
How far down does that go?
It goes infinitely. So this is the first fixed point. All right? This is weird, right? Everybody can see that we're getting deep, right? This is some serious Python stuff. Because we could just tack on .call, and we would always get a method wrapper. So we've hit kind of a fundamental building block of Python here. Uh-huh.
There's always the same instance of a method wrapper, or it does a construction of a method wrapper each time you access stuff.
I believe it's the same instance. Yeah. But you'd have to go into the source code. That's probably an implementation detail, but I think it's the same instance. So, yeah, this is cool. This is cool. This is a fixed point. This is the first one. There's another one today. But first, I want to bring up something that the call function allows us to do. Because call is a method and it takes in self by default, we can use self to have state between method calls. And this allows us to have functions with memory, which is who's taken algorithms? This is great for dynamic programming. So here's an example of a function with state. We've got a class, inc, and we have an init, and we're just going to set the num attribute to 0. And then we're defining a call method. Takes in self, because all methods take in self. We increment the num, and we return it. So now if we create an instance of inc called I, and we call it, we get 1. But now if we call that exact same function again, without doing anything in between, we'll get 2. So this is a function that isn't really a function in the mathematical sense of the term. This function has state. It is not the same every time. This function remembers how many times it's been called. So there's all sorts of really crazy stuff you can do with this. For example, you can do a cached function, right? If your function can remember what it's done in the past, then your function can cache those results. And you could use this to save time, which is exactly what dynamic programming is. So the classic example is Fibonacci solver. If you write Fibonacci the naive way, you end up, I'm not going to draw, I'm not an algorithms professor. You end up with exponential runtime, basically. If you just write the classic fib function, if n equals 1, return 1. If n equals 0, return 1. If n, otherwise return fib of n minus 1 plus fib of n minus 2, right? That's the classic fib function. But because every single time we call this function, we recursively call fib twice, you can kind of see that the computational complexity of calling fib grows exponentially, because the size of this recursion tree that we're going to grow is going to become very big. But we can avoid this by caching results. So here we've got a fib solver class. And upon initialization, we're going to create some memory. 0 maps to 0, 1 maps to 1. And then upon calling an instance of the fib solver, we'll be passed in a num. And then if num is in our memory, just return the memory subnum. So this is the caching here. And then otherwise, set the memory at num to be and then the definition of the Fibonacci sequence. So it might look like we're actually doing the same amount of work here because we're still recursing twice for every iteration. But because we're saving intermediary results, this is going to be linear runtime. So this is actually, I think, probably the best way, if I do say so myself, to write Fibonacci, because it's so clean. You end up with just this single fib instance, but the fib instance is cached. And so you can depend on this fib instance being very fast. Not just fast upon calling it once, but then if you call it again, it'll be faster and faster each time because it's kind of growing its memory as you go. So this is really cool, yeah. All right, this is our other fixed point. Let's just take a look at that. What's happening here? We've got a call method. It takes in self, and then we return self. What is self? Anybody? Yeah. Yeah, the instance of the function itself. So what's going to happen when we... Well, first we create an instance. We call it func. What's going to happen when we call this func? Yeah. The function object. We can call this as many times as we want, and we'll just continue to get that. So this is another kind of fixed point, or as I like to call it. Again, I don't know if that's an actual term. I just kind of made that up. But you can see that it's an identity. No matter how many times we call this function, we're going to get the same thing. So I've never actually seen it done in practice, but I can imagine some really interesting functions where you actually maybe put the arguments in each, instead of comma separating your arguments, you pass each argument into a new call of the function. Really interesting stuff.
What if you did return self and then called self? Would it just
return? Sorry.
It's return self open parenthesis close parenthesis.
What if you called self instead?
Would it just
that would be infinite. You'd get a Stack Overflow error, right? Because what happens when you call self? You call this method. So that's recursion with no base case. Yeah. Pretty cool, huh? Yeah, cool. Yeah. Some people think it's cool. All right. So we've seen two ways of writing functions so far. We've seen def, and we've seen class dunder call. There's a third way, and that is lambda expressions. Who here has written a lambda expression in Python? A couple people. Okay, cool. It's just another way of writing functions. That's all there is to it. Except that these functions are a little bit more constrained. They don't have a name, and they're one line. And they have to be one line. So here we've got an add5 function. It takes a num, and it returns the number plus 5. This function is one line, so it's a candidate for being a lambda. So here is an equivalent function, lambda add5. It equals lambda num colon num plus 5. And what this is saying is, everything to the right of this equals sign evaluates to some function that takes in num and returns that number plus 5. Lambda is a statement that says what follows is a one-line function definition. And everything before the colon are the parameters, and everything after the colon is the result of calling that function. And the two do exactly the same thing. Now, what do you guys think the type of that is? I guess this is not a very interesting question. It's a function. There's no separate type for lambdas. Okay, so now that we know about lambdas, and we know that we can pass functions in as objects, we're ready to go over some functional programming classics. And those functional programming classics are map, reduce, filter, and sort. So let's do map. This is a function that you'll learn to love about Python. What it does is it takes in a function, and an iterable, and it applies that function to everything in the iterable. So here's an example. We've got a string, comma, space, and then we're calling .join on this string. And what that does is you pass in some iterable, and then it separates each element of that iterable with the string. So like, let's say we call like a.join 1, 2, or yeah. The result would be 1, A, 2. And if we passed in 3 here, then we get 1, A, 2, A, 3. So this is the best way to do comma-separated values in Python. You know, it's always annoying if you want to print out something like, 1, comma, 2, comma, 3. And it's so hard, it's so annoying to get rid of that last comma, right? If you just write a for loop that prints each thing, and then prints a comma, then prints each thing, you have to like erase the comma at the end. I mean, who's run into this? Yeah, it's such an annoying problem, and it's so easy to fix, but it's still annoying. So this is the best way to get around that problem. If you use string.join, basically you only get the joining string in the middle. So here we've got comma space dot join range 10. Range 10 is an iterable, and it goes from 0 to 9. So we expect 1, comma 2, comma 3, all the way up to 9. But what we actually get is an error. You might have noticed that here I wrote the things that we were joining with quotes. That's because when you call join, everything that you're joining has to already be a string. And this is just one of those things about Python. They chose to implement it this way. They chose to make it so that everything has to be a string when you're joining it. But range 10 yields numbers, yields integers, not strings. So we get a type error. Sequence item 0, expected string, int found. So how would you guys fix this?
Try casting string onto the list.
Try casting string onto the list. So if we did that, we could do that. We could say comma space dot join string range 10. But what that would do, what would that do? So range 10 is a generator. So what that would probably do is that would print probably just this generator object at 0 by ... It'd probably just print that, because if you try casting a range to a string, you're just going to get the object of the range instead of the individual elements. Good thought, though. Ooh, there we go. Yep. You can. Right, what we really need to do here is convert everything in here to a string. How can we do that? With a map function. We've got a function, the string function, which converts things into strings. If we map that function over every element in this iterable, we get a new iterable where every element is now a string instead of an int. And we get exactly what we expect. So this is probably the number one use. I have written this so many times. Map string, comma, range. Or map string, comma, blank. Because there's a ton of times when you need to cast everything in a list to a float, or a string, or an int. So,
How does this compare to just using a list comprehension and string on?
List comprehension?
Yeah.
It's very similar.
Yeah.
It's similar, but a list comprehension, first of all, it uses more memory. So when you do a list comprehension, you actually make the list. Now there's a way around that. You can do a generator expression, which is basically a list comprehension, but without the list. And that would be effectively the same, yeah.
So map is lably evaluated, or?
Yeah.
Okay.
Yes, and we'll see that later. Any other questions? Okay. Now here we passed in string. You can also pass in any function. So here, in line, I'm defining and passing in a lambda expression, a function basically. So here we're gonna map this function over range 10. And this function says add 5 and then convert to string. So this is a way to compose, what if we wanted to add 5 and do string? Well, this is how you could do it. You could make a new function, a lambda expression, where you call add 5 and then call string on the result. And now if we do this, we get exactly what we expect. Does that make sense? Okay, how about this one? What do you guys think is going to happen?
Print 0 and 1 and then return like none.
None? Maybe. I forget. So, yeah. Basically, I don't actually, I thought it was going to print, but apparently it doesn't. Try this on your own Python interpreter, because I totally, what I was getting at here is basically, you want your function here to return the result, not to do something with the result. So like, you don't see this really, because we're a map. When you call map, you're literally mapping some collection to some other collection. But if your function doesn't return anything, then these arrows are kind of like non-existent. So print returns none. So I think, yeah, if we actually iterated over this map object, we'd get none, none. I'm not sure why it didn't print. That honestly might be a typo, because I think it should. But the point here is that...
When I ran that exact line,
Yeah.
I ran it with 10, but it printed out all the numbers and then a list of nuns.
List of nuns? Okay. When you ran this exact thing,
That one had a bottom.
map, print, range 2?
I got a memory. I did the next one.
Yeah, I got a map object.
I got that.
A map object? Did it print the numbers?
No.
Okay. I don't know why that doesn't print the numbers. But the point is, don't do this, because it didn't do what we expected, basically. It's clear what we meant. Print everything in this range. But that's not what map is for. Map is for mapping from one collection to another collection. And so this function it's not an arrow. It doesn't actually change the value. It just prints it. Okay. The other thing I was getting at here is that you expected none, none, right? You were what you said about lazy evaluation, here you can see it. When you call map, what we get is not actually the result of mapping. We don't actually, calling map doesn't actually do anything. It just creates an object that's prepared to do it. And this is called lazy evaluation. At this point, that's why it doesn't print. That's why it doesn't print, because it's lazy. That's right. Okay. I knew there was a reason. So there's a lot going on here. I should have split this into two things. So map is lazy. And what that means is that it's not going to actually call this on anything in here until we tell it to, until we require something from this expression. But we haven't required anything from this expression. We've just said it. We've just said map this to everything in here. And so what it's returned here is a map object. This is an iterable that is prepared to map print to everything in here, but won't actually do it until we iterate over it. And so that's why we don't actually print anything. It's because we haven't actually done the map yet. Map is a lazy function. Does that make sense? Uh-huh.
Is there any way to know if something's lazy, or is that just something you do?
Basically, in Python, a lot of things are lazy. Python will try to be as lazy as it can, because there's certain performance benefits you can get. One way you'll know if something is lazy is if you print it out and you don't get the actual thing you expected. So you can also look up the function. Other than that, I'm not sure how you would know that it's lazy. Yeah. But anyway, the way to get around this, if we did actually want to print none, none, is we call list. List is, I call these functions accumulators, because what this does is list takes in an iterable, anything that can be iterated over, and it just packs it into a list. And so now we're actually requiring things from this map. We've created the map instance, and now we're saying iterate over this map instance and put everything into a list. So now we get 1, 2, none, none. That's, yeah. So a lot going on in this slide. I should have split this up. But anyway.
What is the none thing?
None. So all functions in Python return something. So if a function appears to be void, what it's actually doing is returning none, which is basically null. So here the print function, we think of it as a void function. It takes in its arguments and it prints those arguments. But there's no such thing as a void function in Python. What it actually does is returns none, which means that the result of mapping this function over this range is none, none. 0 goes to none, 1 goes to none. That's the map. Does that make sense? Kind of cool? This is so useful. You'll learn to love map. It can be abused, though. You end up getting these lines that are just like 400 characters long, and it's like map this to this to this, and then map that, and it's gross. But
I just tried making my own version of this yesterday. Would have been nice to know this already exists.
Your own version of map?
Sort of, yeah.
Yeah. It's a very useful tool. It exists in most languages. It's just Python makes it very easy. It's built in. I don't think you don't even have to import it. So yeah. Okay. Here's another functional programming tool that you'll use a lot: sorting. You might not think of this as a functional programming tool, and it isn't really. I mean, sorting is something that we do in all paradigms. But it benefits greatly from the ability to pass in functions as objects, and we'll see that in just a sec. We've got points. This is a list of point objects, and points just have an x and a y. You can basically ignore this. Named tuple is a class generator. It's actually a great example of metaprogramming, which returns a class which inherits tuple, but where each of the elements in the tuple can be accessed by these names. So here, this object here, 0.01, we could use it like a tuple. We could say, like, let's say x sub 0, or let's say the point is called a. If we access the 0th element of this point, we would get the x value, or we could do a dot x. Those are equivalent. So a named tuple is just a name map to a tuple. It's really useful. You don't have to worry about it, though. Basically, we've got a list of your standard point objects. And let's say we want to sort those points. It's not clear how we want to sort them, right? How would you sort a list of two-dimensional points? You could do it from left to right, top to bottom, distance from the origin. So what was the default here? It looks like we went x equals -4. Yeah, we sorted by x, basically. And this actually is the default Python behavior for sorting tuples. If you sort tuples, a list of tuples in Python, it sorts them by their first element first, and then if there's a tie, it resolves that tie with succeeding elements. And that's what we saw here. X is the first element, so it's sorted by x. Now, what if we want to sort by y? Well, you can pass a key function into the sort function. So this is passing a function in to another function. And this function says, given an element, return the .y of that element. So now, if we do that, it'll sort by y. We got y equals -2, y equals 0, y equals 1, y equals 1. So this is really useful. And then we can even sort by the, I didn't go over the star operator, and we'll cover that later. But basically, this sorts by the distance to the origin. So we get 0, 1, 1, 0, and then these really far away points. Filter is another classic functional function. It takes in a predicate in a sequence. It's very similar to map, but where map took every element and called some function on it, resulting in some other element, filter instead takes every element, checks the predicate of that element, and then if it's true, passes it on. It's a filter. So here's something that we've probably all done. We've got an array. We loop through the array, and then only if I mod 2 equals 0 and the length of the string is less than 2 do we append the I. That's something we've probably all done before. We're just iterating through a list, but then only doing something with the element if it meets some criteria. This is something that we could do really easily with filter. So what we could do instead is filter the array by this predicate. And the predicate is a function that takes in I and then returns true if I mod 2 is equal to 0. And so if we do this, notice I called list on this filter because filter is also lazy. So to actually accumulate everything that got filtered, we'll call list, and we get all the even elements. We could do that with the other predicate too. Length of string is less than 2, right here. We get what we expect. And you can compose these filters too. So and this goes for maps as well. So let's say we filter this predicate over the filter of this predicate and the array. And this is useful because everything that goes on here is lazy. You'll notice I didn't call list. I called list on the result here, but I did not call list on this filter object. That's because we didn't need to. We need to call list here in order to actually see all the elements, because we can only see all the elements when we get them all and put them in a list and print the list out. But here, filter operates on iterables, and a filter object is iterable even if we haven't converted it to a list yet. So this is laziness in action here. Yeah. Does that make sense, everybody? Cool. Okay. All right, one more of these functional functions, reduce. And this one is the hardest to get the hang of. What it does is slightly different from what map and filter do. Map and filter are all about taking a collection and mapping it to some other collection. So map just literally maps every element. Filter selects elements based on the predicate. Reduce is different. It takes the collection and maps it down to a single value. It reduces the dimensionality of our set here. So let's say we want to calculate the sum of the integers up to 9. Pretty straightforward thing. We could just write it out like that. But here's another idea. We could reduce range 10 with this reduction. And what this is saying is, given an a and a b, return the sum of a and b. This is a function that takes in 2 parameters and returns one number. And what reduce is going to do is use this 2-to-1 function to reduce the entire list down to one number. So what this is going to look like is, first, it'll reduce the first 2 elements. And then it'll reduce the result and the next element. So,
Is that at least as hard as writing it out code?
At least as hard. What are you saying? What are you saying? What? Well, what if you wanted to sum everything up to 1 billion? Write a for loop? Well, here I didn't even write a for loop. So it's useful, okay?
Which is at least as hard as writing your for loop.
What is?
Using the reduce.
Using reduce? Well, so reduce is useful for other stuff too. But this is just an example. If you don't want to use reduce and you just want to use for loops, be my guest. I'm just showing you some cool functions here. So, and then this reduces to 3, and then this reduces to 6. So we get 45. What if we wanted to do an alternating sum reduction? For loop, yeah. But what if we wanted to do it in one line? Oh, that'd be so cool. Well, we could write a function that has state, and the state is its sign. And then every time we call it, the sign changes, and we reduce by multiplying by that sign. I don't know. This is how I would do it, but maybe I'm just crazy. I don't know. And then we would reduce using the alternating sum function over the range, and we'd get what we expect. But if you just want to use for loops, yeah, you called me out here. You can do all of this stuff with for loops. It's just kind of fun to do it in one line. I don't know. It's really cool.
That's way more than one line.
Well, yes. That's true.
You could just make it out.
Yes. No, this is useful, I promise. Because basically there are functions that are built in that can act as reducers and maps. So like, for example, the map string example. Yeah, you could do that with a for loop, but I think it's fair to say that it's easier to just say map string over array than it is to say for I in array, string I, out.append, string I, So basically, you're right, this is way more work right now. But that's because I had to write this alternating sum class. If you were using a built-in function, this might make your life easier. It just, all right, whatever. Okay, last topic. How am I doing on time? Oh, shoot. Time flies by. All right, these are generator functions. Generator functions are really interesting because instead of saying return, you say yield. And what that means is that the result of calling this function is actually a generator object. And so this goes back into the lazy programming. What calling a generator does is creates an object that's iterable and is prepared to yield things using your code. So here, this is a random sequence generator. And then for length number of times, we yield random numbers. If we call the random sequence generator and then accumulate it into a list, we get just some random numbers. So, all right. And then you can filter and reduce that, but you guys don't seem very impressed by filter and reduce, so whatever. All right, here's a classic. I'm not going over this. I'm running out of time. Generators can be recursive. So this is a fun little program, which is actually really useful for certain things. Let's say we want to have a program that takes in user input, and your user input might have some dollar signs in it. And we want to then prompt the user for something to substitute into those dollar signs. So here we said lights. Each dollar sign turns into lights. And then here we get prompted for another substitution. So here, let's say food. Then we substitute with that food. But let's say we want to do this recursively. So now we want dollar sign to equal dollar food. And then we set dollar to tasty. We get my tasty food, no less tasty. So does everybody see what's going on here? We get to kind of create arbitrarily many layers of dollar sign substitution, so to speak. And then we can break out of a layer by saying dollar sign break. Does everybody kind of understand this program? More or less? Well, there's lots of ways you could do this, but the simplest way is with generator functions. So here's the code. This is that program. While we're not breaking and dollar sign is in the string, for each substitution of that dollar sign, yield the string but replace the dollar with that substitution. And this is recursive. We've got a generator function. It yields, which then calls the generator function. So we've got, this is how we get the layers of, arbitrarily number of layers of $ substitution. So,
What's the difference between yield and return?
Return just returns a value. And if you use return, it's not a generator function. But if you use yield, what that is saying is this function is a generator function, and the result of calling this function is an iterable, which iterates over each yield statement.
Okay.
Although I'd imagine it would be very bad practice if you have a function that returns in some paths and yields in others.
Yes. If you both yield and return, your function is a generator function, but return means something else. So, and I always forget what it means. I just avoid it. I always just say yield. I always only say return or only say yield. But you can use both. It just returns means something slightly different. Okay. I had to kind of sprint through generators, but that's okay. They're not too important for later topics. I just wanted to talk about functions today because next week it's going to get crazy. And you really have to have your head around the fact that functions are objects in order to fully appreciate next week's lecture. So next week, it's going to get meta. So just prepare yourself. All right. See you guys.